Hello, this video is on rate equations with a specification 3.4.1. Starting off, let's just go over the lesson objectives. By the end of this video, hopefully you'll be able to understand and be able to use rate equations in the form of rate equals a constant called the rate constant K times concentration of reactant A, square brackets give concentration, to the power of M, and that times the concentration of the other reactant B. Again, the square brackets indicate concentration, and B would be to the power of N. So you should be able to write rate equations and calculate K, or calculate one of the other variables in a question. Second lesson objective is to be able to explain qualitatively the effect of changes in temperature on the rate constant. So if temperature increases, does the rate constant increase, or vice versa? First of all, a review of reaction rates from AS and C3. Now, reaction rates are given by the change in the amount of reactants over a given time, or the change in the amount of products over a given time. So we might write this change in reactants over time, or change in products over time. So usually certainly if the reaction is going on in solution, the units for reaction rate would be mole per decimeter cubed, which would be concentration of either reactants or sometimes products, per unit of time. So I'm writing seconds to the -1. So they would usually be the units of reaction rates. So let's just get rid of that, and then we can study. So let's study a reaction where we're going to call a reactant A. We're going to draw a graph of what happens to A over time. So normally in a graph of reaction rates, you would have reactant A and the concentration of A on the y-axis, right? And you would look at the change in reaction rates over time. So what you would normally do is you would start off in the reaction. The concentration of A would gradually decrease until it's all used up. So the reaction rate, as we learned on the previous slide, is the change in A over time. So at the start, a start where time is 0, the reaction rate would be given by the tangent at point 0. Right? So if you draw a tangent here, when you do it you use a ruler, at point 0, you get the reaction rate from this tangent at the point in time that your tangent touches the curve. So that's what the reaction rate tangent would be like at the start of the reaction. And as the reaction proceeds, obviously you get less of A because some of it's turned into product. And so over time, your reaction rate clearly is going to decrease. So after a few seconds, let's say at this point here, right, if you wanted to know the reaction rate at that point there, you would draw a different tangent, right, which crossed the line at that point, and you would take the gradient of that line, and that would give you the reaction rate at this point. Let's call it T1. And similarly, further along, you could take the reaction at this point in time, let's call that T2, and if you drew a tangent at that point in time, that tangent would give you change in concentration over time, therefore reaction rate at this point in time, T2. Okay, we move on now to the rate equation, and it looks quite daunting, but once you get the hang of it, it's not so bad after all. So from GCSE and AS, you know that a reaction rate is proportional to concentration of reactants. Yeah, it's proportional to concentration of A, and it's probably proportional to concentration of B, like that. But instead of writing proportion, what we can do is instead we can use a constant. So this is how the rate equation is used. So rate equation equals now, instead of proportion, and a constant times the concentration of reactant A, also times the concentration of reactant A to the power of M, I'll explain in a minute, and also the concentration of reactant B to a different power, N. M might be the same as N, or it might be different. So as you can see, the rate is proportional to the concentration of A and B to certain powers, but instead of writing proportional, we say equals a constant times that, and that's the rate constant. So a little bit on orders of reaction. Orders in AS level can either be order 0, it could be order 1, or it could be order 2 for each of the reactants. Now, if anything, in fact, is to the power of 0, then it just equals 1. And so what that says, if M equals 0, is that the rate is actually not dependent on the concentration of A. However, if the order of the reaction was 1 for M, then what that says is that the rate is directly proportional to the concentration of A. And so you would get a rate graph where, say, we drew rate against concentration of A, right? And if it's directly proportional, as concentration of A increases, the rate increases by the same amount. And just for completeness, let me do that same chart for an order of 0, where you would have rate of reaction against concentration of A, but 0 if it means that the concentration of A does not affect the rate, and so the rate would carry on at the same rate whatever the concentration of A was. Okay. However, M could also be 2, in which case it's an exponential rate relationship between the rate and concentration of A. Okay, in which case it would look like this, where as you increase the concentration of A, the rate increases by the square of that concentration. So the last thing to say about the rate equation, let me just write it down again. So the rate equation is equal to the rate constant times the concentration of A to the power of N and the concentration of the other reactant, B, to the power of N. Let's just talk about the overall order of the reaction. Let's say you had M equals 1 for the concentration of A and N equals 2 for the with respect to B. Then the overall order of the reaction is just the sum of the two individual orders. So the overall order for that reaction, where M was 1 and N was 2, would be 3. But of course you can in fact have a reaction with 3 reactants, and in which case it would just be rate equals K times A to the power of M, B to the power of N, and then C, the third reactant, to the power of something else. And that could be actually as long as you like, but at A2 you only get up to 3 reactants. There is one other thing to say about the rate equation, and that is that in the rate equation it's not necessarily only reactants and the concentration of those reactants that you can have in the rate equation. Say this reaction was actually catalyzed by acid particles, the hydrogen ions, and that would certainly affect the rate of the reaction, then you can have this rate equation looking like this. So the rate equation would include the concentration of the catalyst to a certain part as well. Right, so now let's have a look at the rate constant and how it's affected by temperature. Let's write down the rate equation, a generic simple rate equation. So we've got rate equals K times the concentration of A to the power of M and the concentration of B to the power of N. And let's consider the same reaction, A plus B going to C plus D. And let's say we do that same reaction at two different temperatures. As we know, the increase in temperature increases the rate of the reaction. But we've done exactly the same thing twice. We've done it first at low temperature and done it second at a high temperature. So the orders are going to be the same and the concentrations are going to be the same, but the rate will have increased. Yeah, the rate will have increased, in which case the explanation must be that K must increase. Okay, so there is a statement of fact for you that K is only constant at a given temperature. And so K varies with temperature, and the bigger K is, the faster the rate is. Okay, so if you remember in the first lesson objective, we needed to understand rate equations. Understanding rate equations includes the ability to write the rate equations for a given reaction. So here we've got an example. The chemical equation below, that's this chemical equation here, shows the acid-catalyzed reaction between propanone and iodine. And so the reaction is first order with respect to propanone, and first order with respect to the catalyst, the hydrogen ions, but zero order with respect to the iodine. Now, what the question is saying is we need to write the rate equation for this reaction. So let's do that on the next slide. That's the question still up there. Now, as you know, we can say the rate equation looks like this, equals the constant times the concentration of the first reaction. Okay, so that's propanone. Right, let's call that to the power of N. And now the question tells us that it's also involving iodine. Let's call that to the power of N. But it also says it is dependent on first order with respect to the hydrogen ion catalyst. Okay, so we have to include the hydrogen ions in the rate equation too, right? And let's, instead of using O, which can be confused with 0, let's call that an X. Okay, so that's our starting point, that first rate equation. And then we look back at the equation and the question and look at what it tells us. It says that the reaction is first order with respect to propanone. So M is going to be 1. Now the question also says that it's first order with respect to hydrogen ions. So X is going to be 1. And it also tells us that it's going to be 0 order with respect to iodine. Okay, so that means N is going to be 0. So we're just going to write that out again. So it's rate constant times concentration of propanone, right? And for M, we're going to write a 1. And then I should have had iodine in there. Iodine, right? And N is 0. And also, let's not forget the catalyst. Okay, so hydrogen ions are in there and X is 1. So that's the next step. We've written out the orders as given in the question. However, we can simplify this. And as you mathematicians will know, that if something is to the power of 1, then we usually just omit the 1. You can leave it there if you want, you won't lose marks, but you don't need it there. And if the power is 0, then so anything to the power 0 is 1, so we can just ignore that iodine. It doesn't take part in the slow step of the reaction, right? So that's order 0, and we don't need it in the rate equation. And also, looking at the catalyst, the hydrogen ions also to the power of 1, so we can write concentration of hydrogen ions on its own without the power. And there you have the rate equation for this reaction, QED. Okay, so the next thing that we need to do often is to calculate the rate constant for a given reaction. And again, we have an example here. So the example is this reaction here, where we've got a second order reaction with respect to nitrogen monoxide, and 0 order with respect to carbon monoxide, and also 0 order with respect to oxygen. So for that reaction, which happens at a certain temperature, it doesn't matter, we're given that the rate is 1.76 times 10 to the minus 3 moles per dm cubed per second, right? And it is that rate when the concentrations of all three reactants are 2.00 times 10 to the minus 3 moles per dm cubed. And so what the question wants us to do is it wants us to find the value of the rate constant at this temperature. So let's work through it. So let's work through this question here. First thing we want to do is we want to write down the rate equation. So the rate is going to be equal to the rate constant times the concentration of the reactants to certain powers. So let's write the first reactant down, nitrogen monoxide, and we're told that it's second order with respect to nitrogen monoxide, so we'll put a little 2 in here. Second reactant is carbon monoxide, and we're told in the question that it is 0 order with respect to carbon monoxide, and our third reactant is oxygen, right? And we're told in the question that it's also 0 order with respect to oxygen, so we put a little 0 up there. There we are, so we have a rate equation. Now the first thing we want to do is recognize that anything to the power of 0 is 1, so we can just ignore carbon monoxide and oxygen as far as the rate equation is concerned. So let's just write that out clearly. So rate equals the constant times concentration of nitrogen monoxide squared. However, the question is asking us for the rate constant, not the rate. Okay, so what we're going to have to do is we're just going to have to rearrange this equation first so that we're left with K on the left hand side. And you can do that algebraically just by dividing both sides by the concentration of nitrogen monoxide squared. So you would get K on the left hand side equals rate divided by concentration of nitrogen monoxide squared, just like that. Now, the next thing, of course, for us to do is to feed in the values that will give us K. All right, so we're just going to look back at the question. First of all, we want to find out what we're told rate is. So we can read here that the rate is 1.76 times 10 to the minus 3. And we look back at the question for the concentration of nitrogen monoxide, and concentration of nitrogen monoxide is 2.00 times 10 to the minus 3. So we're going to put in 2.00 times 10 to the minus 3, but let's not forget the squared. Okay, so squared. And notice I used curly brackets there, or sort of curved brackets there, because it's a number now. Okay, so easy job, put it into your calculator and it comes out at 440. However, we are not finished. 440 what? Of course, we need the units. And that is a very common question, right? So what we're going to do is we're going to work out what the units of K are right now. So the units of K, let's just write that down. Units of K we find by the following method, and you just put the units of each component of the rate equation in. So what are the units of reaction rate? Well, you'll remember that it's change in concentration over time. Okay, so concentration is moles per dm cubed. Over time means we have to put in the seconds to the -1, and that is divided by the concentration of nitrogen monoxide as it happens. So the concentration again is moles per dm cubed, all squared, as in this square here. So next we just simplify the units of K, and we notice that we've got moles per dm cubed once on the top, and we've got moles per dm cubed twice on the bottom. So we can cancel out the squared and the one version up on top, and so that makes it quite easy. Now to get this mole per dm cubed all on one line at the top, we're just going to inverse the indices. And if that maths has you've not done that sort of maths, then we'll deal with that separately. But to get this up to the top, you're just going to inverse the indices. So you're going to have mole to the -1. You're going to have dm cubed, and you've still got your seconds to the -1 there. So that would be the units of K: mole to the -1, dm cubed, seconds to the -1. Done. But just for the sake of completeness, let's write out the whole thing. So the rate was 440, and the units were mole to the -1, dm cubed, seconds to the -1, QED. So that's the end of this lesson. Let's just check that we've covered off everything that we wanted to cover off. First lesson objective was we needed to understand, and by that we mean be able to write the rate equation. So hopefully we know how to write those rate equations, and to be able to use the rate equations, i.e. to find a rate of reaction given various values of K and concentrations, or in fact use the rate equation to find the rate constant. That was the first lesson objective. The second lesson objective was to be able to explain the qualitative effect of changes in temperature on the rate constant K, and we went over the fact that as K increases, the rate increases, and vice versa. Thank you very much. See you in the next lesson.